Okay, so today we're working on beam deflections and we're going to be using the moment area method. So we have a beam drawn here with 2 point loads, one at C, one at D, simply supported at A and B. And we're going to use the moment area method. We're going to look at the angles of rotation at theta A and theta B at each of the supports and calculate the deflections delta 1 and delta 2 at the applied loads, point C and point D respectively. Um, so I've gone ahead, I've used statics to solve for the reactions, which I have down here, and I've labeled those on the free body diagram off to the left. I've set up the page. I'm going to go ahead, use the graphical method to do the shear force bending moment diagram. And if you want to follow along with that, that's great. Otherwise, just fast forward and we'll pick up the logic once we get down to the bending moment diagram divided by the flexural rigidity and the displacement diagram where all the logic happens, and then we'll go into the mechanics of actually doing the calculation. So away we go. We're going to do the shear force diagram. So following the reactions at A, we're going to start at A and we're going to draw up to 100. I'm going to label that in there, and then we're just going to draw across. Constant because there's no forces. We're going to go down to 100, brings us back to 0. From there, we go across. Again, it gets pushed down 200 to minus 200 and across. And then the reaction brings it back up to 0. So we're fairly comfortable with that. Moving straight on to the bending moment diagram, of course, we have constant shear, which means we're going to have a constant slope, constant positive slope to the bending moment diagram. And so that is going to go from 0 up to a positive value that's equal to the area under the curve. So 100 times 5 meters, so 500 kilonewton meters. It stays constant because there's no shear between there and there. And then the negative 200 shear brings it back to 0 at B. Well, my pen's getting a little stuck there. And we have our bending moment diagram. So the bending moment diagram divided by EI, because EI is constant, we can just draw that up. Here, and that would be the 500 kilonewton meters divided by EI, but it's otherwise the same shape. And that's the one we're going to use for calculating or using the moment area method to calculate the various tangents and displacements. So the secret to the moment area method, or where all the logic happens, is in this displacement diagram. So we're going to have to get an approximation, an exaggerated approximation of what the displacement is going to look like. In this case, it's simply supported and the loads are all pushing it down or displacing it down. And it's going to be not quite symmetric between A and B. Most of the loads are off to the right-hand side, so it's going to be slightly more displaced to the right than the left. And we can use the bending moment diagram to help us with the curvatures and everything else, but we just need to be approximate. So I'm going to draw that in as something approximately like that. And this is what we're going to use to apply the bending moment, the moment area method to get displacements and tangents. So if we look back at the question, the first thing it says is it wants the angles of rotation theta A and theta B. So that's fairly straightforward. So we can just draw in, and I'm just going to slide my page up here a little bit so I don't run off the bottom of the page. And we can draw in our tangents. I'm going to change. So the tangent at A, and let's draw in the tangent at B. Okay, I'm gonna have to extend my line down here a little bit. And I'll label that as theta A and this as theta b. And let's see, we're also interested in our points C and D. And if I label our points down here as C1 and D1, we know that the distance between the tangent from A relative to C would be this distance in here. So that is the vertical distance of the tangent from at C with respect to A. And likewise, I can draw it in here. This distance here is the distance of the tangent at D with respect to A. And those are the tools. I guess the only other one that I'm going to probably use is this distance in here, going from the tangent at B with respect to A. And it's important to get the nomenclature correct. As you're probably aware, if the tangent distance at A with respect to B is actually this distance over here, and it clearly is bigger than the tangent distance at B with respect to A. So you want to make sure you get that right so that we don't make a mistake later on. But having identified that, we actually have all of the logic to solve the problem. All we now need to do is to go through the mechanics of the theorem to apply it and calculate what the actual displacements are. So I guess let's do that. So I'm just going to come up here, calculate our theta at A, and we'll start there. So to do that, I'm just going to make a quick representation of my bending moment diagram so that we can show our various distances and calculations and areas on it and follow the logic. Okay, so I just copied and pasted the diagram, the moment diagram, or the M over EI diagram here where we can use it. What I want to do is divide it up a little bit. I'm going to need to have a line here and a line here. And I'm going to identify this as area 1, area 2, and area 3. So I'm just dividing it up into simple prismatic shapes. Then label this. This is the moment, which is 500 kilonewton meters divided by EI. And the distances, I'm not going to rewrite them, but they're the 5 meters, 2.5 meters, 2.5 meters down there. And I'm also going to mark roughly the centroids of those areas because we're going to need to use their moment arm in using the moment area method. And so the first thing we're doing is we're doing theta A, and so we're going to need the moment arms relative to B. So I'm just going to draw these down here so we can see it. So there's and we will label them in accordance with the area. So I'm going to call this one X1, this one X2, this one X3. And because this is largely mechanical, we're just going to get on with solving it. So let's get those values done up here. So we need X1, and X1 is going to be the 5 meters which is the first 2.5 meter sections plus 1/3 of the second 5 meter section, which we can calculate out and we can get 6.667 meters. And then we'll just carry on x2, which is equal to that first 2.5 meters plus 2.5 meters divided by 2, brings us to the centroid of the second section, which is equal to 3.75 meters. And finally, x3, which is equal to 2/3 of the 2.5 meters, or 1.667 meters. And I'm just going to transfer those values down here so we can see them. 1.667 meters, 3.75 meters, and 6.667 meters down there. So we also need to know the magnitudes of areas A1, A2, and A3. So this is, you get a choice. We can plug in the numerical values for E and I and just carry that through all the way, or we can plug it in at a later date. That's the way I've chose to do it, is to plug it in at a later date, but you can plug it in now, plug it in later. It really doesn't matter. That's a personal preference. So let's calculate the magnitudes of the areas. So we'll start here. So area 1 is equal to 1/2 of the height, which is 500 kilonewton meters divided by EI times 5 meters, and gets us to 1250. That would be kilonewton meter squared divided by EI. And we'll do the same thing for A2. Area 2 is a rectangle, so it is the 500 kilonewton meters and multiplied by the base, which is 2.5 meters in this case. That's equal to 1250 kilonewton meter squared divided by EI, and area 3, which is equal to, it's a triangle, so 1/2 the height, again 500 kilonewton meters divided by EI, and the distance 2.5 meters equals to 625 kilonewton meters squared all over EI. So we have our three areas. So what we know, so if we go back down to our displacement diagram, that this value here, which is the vertical distance between the tangent from A, the tangent at B relative to A, is equal to the moment of those areas. So the distance to the centroid from B multiplied by the area of the bending moment diagram divided by EI. So if we follow that through, we have tangent distance of B relative to A is equal to A1 times x1 plus A2 times x2 plus A3 times x3. And plug in our numbers. So from our previous calculations, we have 1250 kilonewton meters squared divided by EI multiplied by its distance, x1, so 6.667 meters plus area 2, which we see is also 1250 kilonewton meters squared divided by EI multiplied by x2, which is 3.75 meters plus area 3, 625 kilonewton meters squared divided by EI times x3, which is 1.667 meters. And I'll just do that in a couple steps so that you can check your numbers if you're plugging them in and you're having difficulty. So at the top we have 8,334 kilonewton meters cubed plus 4688 and kilonewton meters cubed. Have to be summing like units, of course. 1042 kilonewton meters cubed. And that's all divided by EI. So I am going to plug the numbers in here. So we have 200,000 MPa, or multiply that by 10 to the third to put it into compatible units of kilonewtons per meter squared. And I, which is our 1.20, and in this case we're going to multiply it by 10 to the negative 3 to make it meters to the fourth instead of millimeters to the fourth. And that allows us to calculate our answer at distance is 0.0586 meters, which of course is 58.6 millimeters. So from there, using small angles and small deflections and those simplifications, we can figure out what that angle theta A is. And we know that theta A is equal to that distance, tangent distance at B with respect to A, divided by the length between A and B, which is the length in this case. So that's equal to 58.60 millimeters divided by 10,000 millimeters, which is equal to 0.0059, and that's in radians. And if you go ahead and multiply it through by 2 pi, you can convert that to 0.34 degrees clockwise. Okay, so really the second part is going to be almost a mirror of that, but we're going to do A with respect to B. We're going to go through that. If you've got all of this, you can probably go through that fairly quickly, and then we'll get on about calculating the displacement at C and the displacement at D. So I'm just going to scroll up here and give myself a little bit more room. I won't try not to get it all off the screen so you can continue to follow along. Calculate, in this case we're talking about theta B. And I'm going to go and copy and paste my diagram down. Label these X1, X2, X3 to go with areas 1, A2, and A3. So you see all of the moment arms now are from A going towards B. So we flip those around, and we're going to go through the same process. So let's get down the distances, x1, x2, x3. We already have the areas, a1, a2, a3. I won't recalculate those. I'll just go ahead and use them. So let's get those distances. So x1, and that would be equal to 2/3 of the 5 meters along the base of that triangle, along there. It's equal to 3.333 meters. X2 would be equal to that 5-meter initial distance plus half of the 2.5 meters, so 2.5 meters divided by 2 equal to 6.25 meters, and x3 equal to the initial 7.5 meters, that's the 5 meters plus the 2.5 plus 1/3 of the triangle distance, which is 2.5 meters, for a total of 8.333 meters. So as I said, we've already got the areas A1, A2, A3. So I'm just going to use those from the first part of the question and bring them down. So what I need to do is to demonstrate that the tangent distance of A at A with respect to B. So that's tangent distance. So that's over here in the diagram, tangent distance of A with respect to B. And that's equal to, again, A1 x1 plus A2 x2 plus A3 x3. And we'll go ahead, we're bringing the areas down. So 1250 kilonewton meter squared divided by EI multiplied by x1, which is 3.333 meters, plus area 2 is 1250 kilonewton meter squared divided by EI multiplied by x2, which is 6.25 meters, plus our last area, area 3, 625 kilonewton meters squared divided by EI multiplied by our distance, 8.333 meters. I almost ran out of screen. And so we'll just get that summarized down here. So like before, I'm just going to go, it's equal to 4166. I'm going to take my units outside the brackets here just so I don't have to rewrite it a bunch of times. 7813 plus 5,208, close the brackets. So those are kilonewton meter squared. Actually, no, they're kilonewton meters cubed because they've been multiplied through by the distances, and then we have EI in the bottom. So again, you can just copy this from part 1, 200,000 times 10 to the third kilonewtons per meter squared times I, which is 1.20 times 10 to the negative 3 meters to the fourth. And that's equal to 0.072 meters, which is also equal to 72 millimeters. And we're one step away from finishing this little bit. So I'm just going to do our theta at B is equal to our tangent distance at A with respect to B divided by length. And so in that case, that's 72 millimeters divided by, again, 10,000 millimeters, which is the length, the overall length, or the length between A and B, as you like. And that comes up and gives us a value of 0.0076 or 716 radians. And again, you can multiply by 2 pi and convert that to 0.41 degrees. Let's go in that direction. And I can go ahead and put those values in here. So I'll write them in the radian value, 0.00. Oh, sorry, I gotta get the right ones here. So that's theta A, 0.0059 radians. And over here, theta B is 0.00716. So we're getting there. We only have 2 sections left. So that completes part A of the question, which was to get those 2 angles of rotation or curvatures. And the second part is to get the distance of displacement or the deflection at C and at D. So we're just going to calculate our tangent distance at D, and we're going to do it all relative to A in every case in this instance. So T relative to A. And so that distance is shown up here in the diagram right here. And if we have that distance, then we can use some geometry and figure out what the actual deflected deflection, delta 1. So I'm going to copy and paste my M over EI diagram down here for us to use. So we have our M over EI diagram down. And of course, in this instance, we're interested in D, the tangent distance at D. So let me I'm going to label point D in here, so in case we forget where it is. And we're doing it relative to A. So at D going in the direction of A. And so the distances that we want, that point D becomes our baseline. I'll extend that line down there. And we need the tangent distance to there and the tangent distance to there. Area 3 is on the other side, so we're not concerned about that. So I'm just going to label them in here. And we have x1 and x2. And we ignore area 3. So I'm going to go ahead, do it very similar to what we did before. I'm just going to calculate x1. And x1 is going to be equal to our 2.5 meters plus 1/3 of 5 meters, which is the base. And that's equal to 4.167 meters. X2 is equal to half of our 2.5 meter distance, or 2.25 meters. And again, we still have area 1 and area 2 have already been calculated, so we can jump right in and say that our tangent distance, as labeled in our diagram, at D relative to A is going to be equal to A1 times x1 plus A2 times x2 in this case, which is equal to 1250 meters squared divided by EI multiplied by 4.167 meters plus area 2, which is the same 1250 kilonewton meter squared divided by EI and multiplied by x2, which is 1.25 meters. And then that is equal to 5209 plus 1563, all multiplied by kilonewton meters cubed, divided by EI, which as before, 200,000 times 10 to the third kilonewtons per meter squared, and 1.20 times 10 to the minus 3 meters to the fourth, equal to 0.02821 meters, or 28.21 millimeters. So all we have to do now is we have that distance, we have to use the geometry of the problem shown in that displacement diagram to be able to flip it around and to actually get the displacement at point D. So the one thing that I want to do here is I'm going to use our geometry to get our distance D1. And with that overall distance, D1, we can subtract the distance that we just calculated, the tangent distance at D relative to A, from it to get our displacement delta at D. And so we can get this DD1 by saying that's equal to theta A multiplied by the distance, 7.5 meters, which is the distance of D from A. And so that is equal to 0.00586 radians multiplied by 7.5 meters equal to 0.044 meters, or 44 millimeters. And that then allows us to calculate the displacement at D. And I'm just going to go up here and draw that in case. Displacement at D is equal to DD1 minus TD relative to A, and that's equal to 44 millimeters minus 28.21 millimeters, leaving us with a displacement of 15.79 millimeters. And I'm going to go ahead and just draw that in here, 15.79. And so we just have to do that one more time at point C, and then this question will be done. So again, I'm just going to label this up. I'm going to start by calculating the tangent distance at C relative to A. So I'm going to paste my diagram down here and get ready to go. So I'm just going to label up my diagram. So we're interested in point C, which is here. And we're doing it relative to A, so looking between A and C, so we only have one area to concern ourselves with, which gives us one distance. So that's that distance in here. We'll call that x1. And that's going to make our things go a little faster. We have x1, which is equal to 1/3 of the base, which is 5 meters, which is equal to 1.667 meters. We know area 1, so our tangent distance at C relative to A is equal to A1x1, which is equal to 1250 kilonewton meter squared divided by EI multiplied by the distance 1.667 meters. (2084 kilonewton meters cubed) divided by, and again our EI hasn't changed, times 10 to the third kilonewtons per meter squared, and our 1.20 times 10 to the negative 3 meters to the fourth, so we extend that out there, gives us distance of 0.00868 meters, or 8.68 millimeters. And as before, we can use our geometry. So I'll just write that in here, use geometry to get CC1. So I'm just going to scroll up here a little bit so you can see what we're doing. We have CC1. You can see the distance in there. Ultimately, we're interested in this distance in here. We'll call that delta at C. So we're going to go CC1, and that's equal to theta at A multiplied by its distance between A and C, which is 5 meters. So we'll go 5 meters, and that's equal to 0.00586 radians times 5 meters, which is equal to 0.0293 meters, or 29.3 millimeters. And that allows us to calculate our displacement at C, which is equal to the distance CC1 minus tangent distance at C relative to A, which is equal to 29.3 millimeters minus 8.68 millimeters, or 20.62 millimeters. And that's it. With that, we've answered all the questions posed. We've done that using the moment area method, and it's a really great technique. Of course, it ties in nicely with the method of successive integrations because it's using that same curvature relationship. But really, it's a technique, and it allows you to comprehend a little bit more how it all comes together. And the problem solving for this all happens in that displacement diagram right there. So if you can get to that displacement diagram and decipher it because you can appreciate or understand how important the supports are with where their tangents go, whether it's a fixed support or a pin support, it unlocks the geometry, which allows you to apply the two theorems in order to solve the problem. So with that, I'll sign off and go on to the next problem, and I hope this has been helpful to you.